Welcome to the Soil Mechanics movies of Delft University of Technology. My name is Phil Varden and today I'm going to talk about the Triaxial test. The Triaxial test is one of the most versatile and widely performed geotechnical laboratory tests, which allows you to determine the shear strength of a soil for use in geotechnical design. Here you see an example of the engineering application of the test. The dike loads the soil, which provides strength, but the weight of the soil also creates an overturning moment which acts to fail the dike along the slip plane shown. When the critical strength of a soil is reached, a failure mechanism can occur that leads to a slip surface. The Triaxial test provides strength information of a soil under specific confining pressures, for example like the specimen shown here at the top of a dike. The primary parameters that we obtain from the test are the angle of friction, phi, and the cohesion, C, or in some cases, just the undrained shear strength, SU. These parameters are decisive in determining the shear strength of a soil. The shear strength is then determined using the theory of the Moore-Coulomb failure envelope. Here you see a picture of the Triaxial test apparatus that we use in the lab. The soil specimen that we want to test is located in the Triaxial cell. The Triaxial cell is placed in the load frame. The applied load is measured and displayed by the load gauge. The pressure inside the Triaxial cell is measured and regulated and displayed by the cell pressure gauge. The pore pressure in the soil specimen is measured and displayed by the pore pressure gauge. Lastly, the displacement gauge shows the vertical displacement during loading. Now let's take a look at the Triaxial cell in more detail. The soil sample is placed between a top cap and permeable plate, allowing for pore pressure control and measurement. The soil sample is sealed in a rubber impermeable membrane. This membrane separates the pore fluid from the fluid in the cell. At the top of an axial force can be applied via the load ram, and the vertical deformation is measured via the displacement gauge. Again, we see the two gauges measuring the pore pressure and cell pressure. There is a valve that controls the drainage of the pore fluid. This valve can either be closed or opened. This drainage valve is very important for the type of Triaxial test and will be discussed later in this video. We have two main phases in the Triaxial test. The first phase is the consolidation phase. In this phase, the cell pressure is increased via the cell fluid, which gives a uniform confining stress. This is also the smallest normal stress in the sample, so it is called the minor principal stress, or sigma 3. Whether the soil is allowed to consolidate depends on the type of Triaxial test. This will be discussed later. The second phase of the test is the shear phase. In this phase, an axial stress is applied via the load ram to the top of the soil specimen. This stress is called the deviator stress. So on the top of the sample, the sum of the deviator and the confining pressure is applied. This is then the largest normal stress, so is called the major principal stress, or sigma 1. There are three types of Triaxial test. The tests are distinguished by the pore fluid drainage conditions applied during phase 1 and phase 2. During the consolidation phase, a uniform confining stress, sigma 3, is applied to the soil specimen. During this phase, we can either open or close the pore fluid drainage valve. If the valve is open, the pore fluid is allowed to drain, resulting in consolidation of the soil specimen. We call this test consolidated and use the letter C. In this case, no excess pore pressures will build up and the soil specimen volume will change. If the valve is closed, the pore fluid is not allowed to drain and pore pressures increase, resulting in an unconsolidated soil specimen. We call this test unconsolidated and use the letter U. In this case, excess pore pressure will remain and the soil specimen volume will not change. During the shear phase, the deviator stress is applied to the soil specimen. Again, during this phase, we can have the control valve either open or closed. If the valve is open, the pore fluid is allowed to drain. We call this test drained and use the letter D. In this case, excess pore pressure will dissipate. The test needs to be done slowly enough to ensure drainage is able to occur. If the valve is closed, the pore fluid is not allowed to drain. We call this test undrained and use the letter U. In this case, excess pore pressures will develop. These could be positive or negative. By measuring the pore pressure in the sample, we're able to compute the effective stresses. This test can be done quickly and is therefore a commonly used test. So together there are three types of triaxial test: consolidated undrained, CU, consolidated drained, CD, unconsolidated undrained, UU. The UU test is the simplest and fastest test to perform, as in this case only total stresses are recorded and controlled. For the next part of this video, we'll look at the stresses on the soil sample, the Moore's circle and Moore Coulomb failure envelope of the UU test. The purpose of this test is to determine the undrained shear strength of the soil. Remember that throughout this test, the pore fluid drainage valve is closed. Initially, there is no stress applied to the soil, so the Moore's circle is a point on the origin of the Moore Coulomb diagram, as you see here. In phase 1, the consolidation phase, a cell pressure is applied to the soil specimen. As only the cell pressure acts on the soil specimen, the Moore's circle remains a single point on the Moore Coulomb diagram as sigma 1 and sigma 3 are equal. Note that these are total stresses. In the unconsolidated test, the drain remains shut and consolidation is not allowed to occur, even though this is called the consolidation phase. After phase 1 is complete, the second phase starts by applying the deviator stress, which increases sigma 1. During shearing, the minor principal stress, sigma 3, does not change. We continue to increase the deviator stress until the specimen fails. The Moore's circle then becomes larger. The shear stress at failure is the undrained shear strength, which is equal to the radius of the Moore's circle. Remember that during this test, the drainage valve is always closed. Therefore, the effective stress typically does not increase. A consequence of this is that the soil sample will not gain any strength in the consolidation phase and always fails under the same deviator stress, independent of the cell pressure that is applied. If, for example, we apply this sigma 3 during the consolidation stage and the drainage valve remains closed, the soil will not gain any strength. After phase 2, the undrained shear strength will be the same as in the previous test. If we plot the failure envelope, it would have an angle of friction of 0 and will have the shear strength then SU. In this example, the two samples were subjected to different cell pressures, and we found that Moore's circles have the same size. The effective stress, sigma dash, in a soil sample is the total stress minus the pore water pressure. The higher cell pressure also has a higher pore pressure, and therefore there is only one effective stress Moore's circle. So again, increasing the cell pressure without allowing drainage has the effect of increasing the pore pressure with no change in effective stress. An identical strength is obtained for all confining stresses. To summarize, the triaxial test allows you to determine the shear strength of a soil for the use in geotechnical design. We distinguish between three types of triaxial test: consolidated undrained, or CU, consolidated drained, or CD, unconsolidated undrained, UU. In the UU test, no drainage is allowed during both the consolidation and the shear phase. This allows us to determine the undrained shear strength of the soil. This is the end of this movie about triaxial testing and the UU test. For more movies on soil mechanics, click on the following link or find our account on YouTube.